Good morning. My name is Luca Chiaraviglio. I am an associate professor at the University of Tor Vergata and a research associate at CNIT. And I'm going to present a talk about the minimum cost design of cellular architectures to serve rural area. And I will explain during this talk both the formulation and the solution that we have found. So I will go very briefly into the introduction since the other speaker have already say explained well the main aspect of community of connectivity in rural area. And in particular, although the interpretation rate are pretty high, and although the most of the population in the world is already covered by cellular network signal, there are at least 2 million people that are currently experiencing a complete lack of wireless cellular coverage. And this is a huge problem. And the connectivity divide essentially emerge in people living in rural and low-income area in the world, since in general the telecommunication infrastructure is more oriented in urban zones, so more ready to be deployed in urban zones, rather than in rural and low-income area. And the reason is pretty simple because in general, urban zones are the most promising one in order to, let's say, deliver connectivity because it's where the people are living, where the people are connecting, and where, in general, the cost can be compensated by the gain. Okay, and this is true for all the cellular network technologies, including the forthcoming 5G technology. So, in order to reduce the cost of the cellular network infrastructure, we propose a new architecture that is actually tailored to serving rural and low-income areas. The idea is pretty simple. The idea is that we concentrate on portions of territory where the users are located, and these portions of territory are typically served by unmanned aerial vehicles, UAV, and on top, so on board of each unmanned aerial vehicle, there are a subset of cellular equipment that are deployed in order to provide the cellular signal. And in particular, the high-level base station functionalities are hosted on dedicated hardware and commodity hardware at the ground site. So there is a ground site which hosts some cellular network equipment, while the low-level base station functionalities are carried on the dedicated hardware on board the UAV. So the scheme reported on bottom of this slide show the actual architecture that we are going to examine in this work. So basically we have an area that represents the coverage area where basically we need to serve users where we need the cellular network connectivity. This area is served by means of UAV that carry only a portion of the cellular network equipment, so typically carry dedicated hardware. Then there is a radio link between the UAV and the ground site, which instead hosts the remaining set of cellular network equipment. So in particular, we host commodity hardware and dedicated hardware. So this is the first step. The second step is that actually this ground site needs to be interconnected. So in this work, we assume that the ground site are connected by means of optical fiber. And in general, in order to enhance reliability, in order to provide a good level of reliability, these sites are connected by optical fiber in order to form an optical ring. Okay, so we need to let's say establish a ring between the installed ground site. And the third ingredient of this architecture is the fact that each ground site and each UAV takes its energy solely from renewable energy sources. So each ground site has to implement what is called an energy balance, according to which the battery level at current slot is typically the combination of the battery level at premium slot, time -1, the energy that is derived from solar panels, if it is available, And then there are some consumption due to the fact that the site itself consumes some energy consumption, and due to the fact that the UAV at one point needs to be recharged. So the key question that we target are the following. So in particular, we want to select the places in order to install the ground site. So where to install the ground site, given a set of candidate one. The second question is the links. So which fiber links need to be installed in our architecture? So where to install this link? The third question is how to properly dimension each site in terms of installed solar panels and batteries. And the third question is the association of the UAV to the site in order to minimize the total cost. So, and at the same time, also covering the set of area. So the contribution are reported here. So basically, we target the minimization of the capex installation cost in a UAV-based cellular architecture. And we proposed an optimization-based framework to tackle the problem. And our optimization problem is able to, first of all, select the ground site and the links that need to be installed, dimensioning each site in terms of solar panel and batteries in order to ensure the level of energy to recharge the UAV and also to provide energy to the site itself. And finally, scheduling the UAV association to the area and their recharge on the ground site. So the problem is pretty complex. And in order to solve the problem for large instances, we also propose an efficient algorithm that is briefly introduced in this talk, while the details are reported in the reference at the end of this presentation. And finally, we compare the optimal formulation, the algorithm, and a reference algorithm in different scenarios that are located in a rural area of Italy. So here you have the problem formulation. So we start from the set definition. So I'm going to be, let's say, pretty detailed, but I want to give you also to provide you the main intuition about the formulation and why it is so complex to optimize the cellular connectivity in rural zone. So in particular, we start from the set definition. So A is the set of area to be covered, S is the set of candidate site, D is the set of available UAV, T is the set of the slot, and E is the set of candidate link among the candidate site. Then we start including the basic constraint of our problem. So the first constraint is about the coverage of an area. So let us introduce an input parameter called GSA, which takes value 1 if a UAV is connected to site S is able to cover area A, 0 otherwise. This can be set, for example, based on a maximum distance or whatever we want. So basically, we have this big matrix. And then we have the variable XSDA of T, which take value 1 if UAV D is connected to site S, cover the area A at a slot T, 0 otherwise. Okay? So basically, this is a variable that is managed by our optimization problem. And the area coverage constraint states that each area in each slot needs to be covered by one UAV. So basically, we have this first constraint. So basically, we provide the full coverage of the area that needs to be covered. Okay. Then the second constraint is about recharging. So basically, we introduce variable RTSD. We take value 1 if UAV is recharging on site S at time t, 0 otherwise. And basically, with this constraint, we impose that each UAV in each slot can be recharged in at most one site at the same time. Then, in the following step, we introduce the recharging in installed node constraint. So basically, if we have a recharging action, we need to install a site, okay? So basically, we need to set up this variable ys, which take value 1 if candidate site S is installed 0 otherwise. And in this way, we control the sites that are installed. Then, another condition which triggers the installation on the site is when the site is used in order to host cellular network equipment. And in particular, this is, let's say, ensured for this constraint. So in particular, If there is a UAV that is connected to a site in a given time slot, then that site needs to be installed also, because the site is used to host cellular network equipment. And finally, we have introduced auxiliary variable xDAT in order to essentially consider the case that each UAV, each area, each time slot is covered or not. And basically, this with this constraint, we set up this xDAT variable. Okay. Then the following constraint is about the action that each UAV can do. So basically, each UAV in a given time slot can either covering, and this is the first term, or recharging. And basically, we have that this summation is equal to 1 because UAV can either be covering, either recharging. Not that this can be even complicated. So, for example, in a given task slot, UAV may be not also used, and we just have to include another variable in this summation. But in this formulation, we consider the simple case in which each UAV is either covering, either recharging. And then in the following, we impose the constraint that if a UAV was covering in the previous task slot, then in the current time slot, the UAV has to be recharged. Again, this is a simplification that can be, let's say, make more complex. We will show that actually this simplification allows to control the UAV action in a very simple way, because basically the UAV, after that has performed a coverage of an area, it needs to come back to a given site in order to be recharged. And then we impose in the following constraint the energy balance, the energy that is required, on each site. Basically, we introduce input parameter EDR, which is the amount of energy needed to recharge UAV-D. We also have input parameter ESF, which is the fixed energy consumption of site S that is needed to keep powered on the commodity hardware and the optical equipment. So this is the energy consumption of the site. And then we introduce variable EST, which is the total energy consumed by site S at time slot T. So basically, the total energy consumed in each time slot by the site is equal to the energy that is required by the UAV in order to be recharged, and the energy that is required by the site. Okay, and we basically introduce in the following constraint the battery balance. So basically, we have that the battery level at current time slot is equal to the battery level at previous time slot plus the energy that is produced by solar panels minus the energy that is required in order to recharge the UAV and to power on the site, minus a compensation variable ESSUT, which actually store the surplus of energy that can be used for other purposes, like, for example, providing electricity for the user that live in proximity to the site or other need. And in expressing this, let's say, compensation, we introduce the variable BST, which actually stores the battery level of site S at a slot T. We have also an input parameter ESP of T, which is the amount of energy that is generated by one solar panel at a slot T. We have also a variable NSSP, which stores the number of solar panels installed at site S. We have as well a variable NSB, which stores the number of batteries installed at site S. And finally, we have the variable for the surplus and the input parameters Bmax and Bmin, which are the minimum and maximum battery level, because actually the second and third constraint for the battery level is that the battery level needs to be lower than the maximum value and higher than the minimum, okay? And in this way, we have assured that each site is able to satisfy the demand to recharge the UAV and at the same time the fixed power consumption that is needed to power on the site itself, okay? Then we also set an initial battery level. So at the beginning, we know that the battery are completely charged. So we have that the maximum value is imposed. And then we also control the number of installed batteries and number of installed solar panel by imposing that this number has to be lower than maximum value, okay? Because, for example, we have some technological constraint that prevent to install a huge number of batteries, a huge number of solar panels, so we control also this installation. And then we also impose the number, or we compute the number of use UAV in this way. So basically, we introduce a binary variable of gamma D, which take value 1 if the UAV D is used in a time slot 0 otherwise. And basically, this gamma is activated if the UAV is either covering, either recharging, and then we compute the number of used UAV as the summation over all the gamma D variable. Then, in the following, we introduced the constraint about the connection site, and in particular, we impose the optical ring installation constraint. The first constraint reported here makes sure that the total number of installed links, which are basically controlled by variable fss prime. So the total number of installed links is equal to 2 times ys, which is the number, which is actually the variable storing the fact that the site is installed or not. So this is the constraint about the number of links. But this is not enough. This is not sufficient in order to make sure that we have a ring, because this constraint may be satisfied even if we have 2 distinct sub-rings, okay? While in this case, we want to make sure that there is a unique ring, so we don't have other structure like trees and so on. So what happens is that we need to impose a second constraint, which is a little bit tricky, because actually we basically make sure that all the links that are installed, okay, and considering S minus set, where S minus is the subset of the links that are installed. So S hat is the subset of installed site. So the site for which ys is equal to 1. Okay. With this constraint, we make sure that all these subset S minus, which are included in S prime but are not equal to S hat, all these subset, the number of installed link is all or equal than S minus minus 1, because in this way we prevent the formation of disjoint ring, and in this way we make sure that the only, let's say, case in which this constraint hold is for exactly S hat, okay? So this is the idea. And there is another issue when imposing the constraint, because this is actually a runtime constraint, because actually X hat is the subset of sites that are installed that are covered by our problem. And I'm going to show you in a while how we can deal with such constraint in a practical way. Then the objective function of the whole problem is defined as follows. So we want to minimize the total cost that are expressed in terms of cost for installed batteries, cost for installed solar panel, cost for installed site, cost for used UAV, and cost for deploying the optical ring. And then I'm going to show you in the following how to solve this problem that we called optimal design. So in particular, we basically build the initial problem in which basically these constraints are not included. So basically, we start with 18, and then we solve this problem. We check if the current problem includes only one ring of installed links. If the ring is not is enforced, so if we have, for example, two disjoint ring or a destructor, we basically start the site and we generate the S hat set, and then we add the constraint 19, so this one, runtime, to the problem, and we basically iterate, we solve again the problem, and we check again if we have got if we got a single ring or not. So basically, it's a kind of iteration over the instances of the problem. Then, together with the optimal formulation, we also derived a suboptimal algorithm that we call DRIs. And the main intuition are reported here, while the whole algorithm description, due to the length of time, is not reported here. But I have put a reference in the slide of this presentation, from which you can download the paper and get the algorithm detail. So the main intuition are the following. So first of all, the selection of the pool of installed site is done by applying an unsupervised machine learning-based approach, which exploits a clustering technique. Then, basically, the output of this step is a set of possible solutions in terms of installed site, which need to be pruned in a second step in order to make sure that we consider only feasible solution, so solution that guarantee coverage of the area. Then the first step is the optical ring computation. So given the set of the installed site, we compute the optical ring. And then we dimension each site in terms of solar panels and batteries, of course, each installed site. And finally, we select the minimum cost solution and we iterate over this, okay? In order to assess the performance of the proposed solution, so the optimal formulation and the algorithm, we generate a scenario, a set of scenario. So we start with this, which is called the Frascati small scenario. Frascati is a rural area close to Rome that we basically selected because we get some important information to set the input parameter. In particular, this figure reports the location of the candidate site and also the center of the area that are collocated. So we assume that each of these points can be either hosting a site and at the same time be the center of an area to be covered. We also assume a Voronoi tessellation in order to express the coverage sites, the coverage area. And then this figure on the right reports instead the linked installation cost, CFS as prime, among all the possible site pair. And of course, here the diagonal has cost 0 because a site has cost 0 to be attached to itself, but these are not exploited. While if you consider the other element, there are cases in which the cost may be really high. And this is especially true, for example, when we need, like for example here, we need to traverse historical center in which the cost of the fiber is really high. Okay, so the takeaway of this figure is that actually the costs are very non-uniform. They are very different across the possible site pair. Then the table on bottom report the setting on the other main parameters. So basically, we have information about the power consumption, the energy consumption of the site. We have information, which is this one. We have information about the recharging of a single UAV, which is this one. Minimum, maximum battery level, maximum number of installed batteries, maximum number of installed solar panel, energy consumption produced, produced by the solar panel, which is based on historical data. Number of areas and number of sites, which is equal to 10, cost of a site, cost for a UAV, cost for a solar panel, and finally cost of a single battery. Let's see the result. So basically, this first figure report the center of the area in point, which are basically collocated with this red cross, which represent the covering. So basically, all the area are covered. This light blue line represent the coverage boundaries of each area, which I remind you is simply a Voronoi tessellation. And then we have that with blue, dark blue color, we have highlighted the set of installed sites with cycles and the set of optical links. And you can see here that there is an optical ring composed of 3 rings. So basically here is the solution of the optimal formulation, which is exactly the same as the algorithm. So also the RISE is able to get this solution. The figure on the right here reports instead the battery level evolution for the installed site. So you can see that the battery level versus the times of index typically as a trend which resemble a high and low level values. So we have first high values and then low levels. And this is due to the fact that during the day we have the production of the solar panel, which tend to recharge the batteries, while during the night we have instead the fact that the battery level is decreased because we need to use energy in order to power the site in order to recharge the EV. And you can see in any case that our problem is able to ensure the battery level between minimum value, which in this case is around 1 kilowatt power, 10 kilowatt power, sorry, and maximum battery value, and maximum value, which in this case is equal to something that more than watt hour. By the way, this is the global battery level of a site. So we know that the battery level of the single battery is equal to 0.72 kilowatt hour. But in this case, we have that each site basically installed more than one battery, and so the minimum battery level is higher than 0.72 kilowatt hour. Then the table on the bottom here reports instead the cost, the breakdown of the cost by comparing optimal design, which is our formulation, GRISE, which is our proposed algorithm, and a reference design, which instead assume the installation of optical rings and sites for each area. So basically, it will install a huge amount of fixed equipment. It will not exploit at all UAV, okay, and also batteries and solar panel. So basically, you can see that at the end, the total cost of the reference design is equal to 700 kilo euro, while the cost of optical design and DRIs are consistently lower, and they're equal to 400. And moreover, you can see that DRIs is pretty close to optical design. Then, we are also considering a big scenario in the same area of Frascati, in which we have basically increased the number of areas up to 41. So this figure reports the location of the candidate site and the center of the area. This other figure on the right reports the links installation cost among all the possible site pair. And finally, the table on the bottom reports the parameter setting in which the main change with respect to the Frascati small scenario is due to the number of area and number of sites which has increased, now is equal to 41, and also the maximum number of batteries and maximum number of solar panels, which we assume in this case is equal to 30. Now let's see the result. So in this case, it's not possible to solve anymore the optimal solution, optical design, because the problem is too complex. So the outcome that is reported here in terms of installed site and covered area is the outcome of the DRISE, so the implemented algorithm. And you can see that the DRISE here has generated a link connecting the different sites that are installed. And moreover, by comparing the DRISE with respect to the reference design, we can see that the DRISE is able to notably decrease the total cost compared to the reference design, in which, I remind, each candidate area has to install a site, and all the site needs to make connected through an optical ring. So in conclusion, we have targeted the problem of minimizing the total cost of a UAV-based cellular architecture, which is able to provide coverage for a set of rural area. We have included the site installation cost, as well as the cost of solar panels, the batteries, the UAV, and the optical ring among the installed site. Our results indicate that this architecture is promising in terms of reduction of total cost with respect to a reference architecture that do not assume the exploitation of UAV. And clearly, this is a first step, because future work, it would be important also to target the OPEX cost. For example, the energy consumed by moving to UAV, or the maintenance cost in order to make sure that the UAV are able to work. It would be also good to face the climate event. So, for example, in order to, let's say, assess the impact of wind, of rain on the coverage level. And finally, another solution that may be investigated could be, for example, to consider different level of UAV, for example, low altitude platform and high altitude platform. So I thank you with this slide, and I report you also the reference of this paper, where you can find full detail about the optimal formulation, the algorithm, and the result. Thank you.